So Unit 1 was all about inverses and modeling with functions. So we started off with a definition of relation and in Unit 1.1, we were able to differentiate between relations and functions by analyzing coordinate points, tables, and graphs. So the essential question for this part of the unit was, how do you determine whether a relation is a function? What test do you implement? So, a relation is a mathematical term that describes how two quantities are related to each other by some rule of correspondence. So, the example that I gave in class was, I have two sisters. We are therefore related by some rule of correspondence. We share the same mother. A function, however, is a special type of relation in which each input has a single output. So, in a function, every x has exactly one y. The example that I use is people with birthdays. So there are four characteristics of a function, and these are the formal definitions. So number one says each element in A, which we call our domain, must be matched with an element in B. Number two says some elements in B, which is our range, may be matched with an element in A. Three says two or more elements in A may be matched with the same element in B. And lastly, number four says an element in A cannot be matched with two different elements in B. So in our own words, here's how I would describe a function. Every x must be matched with a y, right? You can't have a person who doesn't have a birthday. Some y's don't have to be matched with an x. There could be a day that nobody was born. Now, in the world, that's extremely unlikely, but say you took our class, for example. With only 20 students, there's a very high chance that there are some days of the year that aren't matched with a person who has that day as their birthday. Number three says two x's, or two people, can be matched with the same y. So it makes sense that it's okay that two people have the same birthday. But number four says the same person cannot have two different Ys or two different birthdays. So here's an example of time of day and temperature. Which of these sets would be our domain? Time of day. So our domain is actually the numbers 1, 2, 3, 4, 5, and 6. That means that the temperature has to be our range. And our range is only those that are circled, so 9, 13, 15, 12, and 10. So is this a function? Well, let's go through our characteristics of a function. Number one says every x has to be matched with a y. So does every time of day have a temperature? Yeah. All right, so let's go to number two. Number two says it's okay if some of our y values aren't matched with an x, which is what we see here with the numbers on the far right that aren't circled. So 1, 2, 3, 4, 5, 6, 7, 8, 11, 14, and 16 are all examples of y's that are not matched with an x. So again, we're still good. Number three says it's okay if two different x's go to the same y. Where do we see that here? With 3 and 4. So at 3 p.m. and at 4 p.m., it's 15 degrees Celsius. Does this make sense? Is it okay that at two different times of day, you'll get the same temperature? Yeah. When you wake up, maybe at 9 a.m., it could be 50 degrees. And then it also cools back down at night, so it could be the same degrees at 5 p.m. as well. But lastly, number four says that you can't have one time of day have two different temperatures. And that makes logical sense. At 4 o'clock in the afternoon, it can't be 30 degrees and also 80 degrees. It has to be one or the other. So yes, this is a function. And to write this relation as a set of ordered pairs, we use the squiggly brackets and then write each of the coordinate pairs. So 1, 9, 2, 13, 4, 15, 3, 15, 5, 12, and 6, 10. The order doesn't matter. So let's look at the example on the left. We see 2, 9, 4, 5, and 11, 5. Again, all of our x's are matched. In this case, there's no place where a y is not matched. We don't have a place where one x goes to two y's, and we do have a place where two x's go to one y. So to help me remember this, it is okay if the arrows converge, but it's not okay if they diverge. So in this case, 4 and 11 are going to number 5. They're converging at 5, but it would not be a function if there was a double arrow at, say, 4 going to both 9 and 5. So yes, this is a function because it fits all our characteristics. Go ahead and try the one on the right on your own. So the vertical line test is a test used to determine if a relation is a function. A relation is a function if there are no vertical lines that intersect the graph at more than one point. In other words, if a vertical line crosses your graph more than once, it is not a function. Why? What characteristic of a function is that breaking? If I draw a vertical line, like this one on the left, I have a vertical line at x equals -2, let's say. At -2, that graph crosses twice, which means I have 2 points that have that same x value, one in the negatives in that third quadrant and one in the positives in the second quadrant. So no, that circle is not a function. The middle one, though, no matter where I draw that vertical line, it only crosses once, so that is a function. And on the right-hand side, it is not a function, because when I draw my vertical line anywhere, it again crosses twice. So in summary, all functions are relations. Relations is an umbrella term, but not all relations are functions. In Unit 1.2, Parent Functions and Transformations, we were able to apply transformations to the 10 parent functions that we have memorized. The essential question for this part of the unit was how do we use our knowledge of parent functions to describe and graph transformations? So we're going to try and transition from a y equals x mentality to a function notation, where instead of calling all of our functions y equals y equals y equals, we're going to use f of x, or g of x, or k of x to differentiate between the functions that we're using. If we referred to all of them as y equals y equals y equals, we would never be able to tell which one we were referring to. But by using function notation and giving each equation a distinct function notation, we're able to clearly differentiate between whether we're talking about q of x, k of x, m of x, f of x. So these at the bottom are a lot of our examples of our parent functions. We see quadratics, which are the U shape, square roots, which are kind of a U turned on its side, rationals, which are very odd, but we're going to get to them in Unit 4, linear, just a line, polynomials, which include cubics and additional degreed polynomials, exponentials, which grow incredibly fast. So as x increases, your y shoots up really fast. But the ones that are not on here include absolute value, which is shaped like a V. It's the one with the 2 bars on either side. So let's review our relation and function before we get into parent functions and their transformations. What's the domain of this function? If you said it's the numbers on the left, you're correct. So that means that the range has to be the numbers on the right. So the next question is this a function? Well, let's go through our characteristics of functions again. All x's must be matched with a y, which we see. All of our x's have an arrow to somewhere. Number 2 said that it's okay if some of our y's don't have an x. In this case, all of our y's have an x, so we're still okay. Number 3 said it's okay if 2 different x's go to the same y. And we see that at x is 1 and x is 2. Both of those arrows converge at 4. But the last characteristic of a function says that you can't have one x go to 2 different y's. So that means that this thing cannot be a function because 1 goes to both 3 and 4. That would be the same as me having more than one birthday. Can't happen. So here are the transformations that we've talked about. A number on the outside, so a plus or minus k, moves the graph up or down. A number on the inside, plus or minus h, moves the graph left or right. Keep in mind, a number on the inside is a little tricky. If it's positive, you'll think that it's going right, but it's actually going to go left. This is not the case for up and down. If it's a positive on the outside, it's going to go up. If it's a negative on the outside, it's going to go down. But if it's a positive on the inside, it's going to go left. And if it's a negative on the inside, it's going to go right. The last of our rigid transformations is a negative in front. This means that I vertically flip about the x-axis. So instead of a u, or a valley of a quadratic, negative x squared would look like a hill. These are all rigid transformations because I'm not changing the overall shape of my function. I'm just picking it up and moving it up, down, left, right, or upside down. Our non-rigid transformations, though, change how narrow or wide they are. So if there's a number being multiplied in front of the function, for example, 5x squared or 3x cubed, that's going to make it a vertical stretch, which means it's going to get a little skinnier. However, if the number in front is a fraction, it's going to make my shape a little bit wider. It's important to note, though, that sometimes you'll have both a reflection and a stretch or compression. For example, something like negative 3x cubed. This does not mean that the negative 3 means a compression. That means that there are simply two transformations happening. One is the negative, which is causing the reflection, and two is the 3, which is causing the stretch. So to help us kind of solidify our understandings, there are three different colors corresponding to the different ways a function can move. The A, or the number in front, tells us whether it's right side up or upside down, and how skinny or tall and fat it is. The H on the inside determines right and left, and the K on the outside controls up and down. So I've used an example of a quadratic and a cubic, but you can perform these transformations with all 10 parent functions. So let's do this example together. It says, graph the parent function and the transformed function of h of x equals 3x minus 4 squared plus 1. So if I got rid of all of the numbers around that function, I would just be left with a quadratic, or y equals x squared. Therefore, there are three things happening because I see three numbers that I would have had to get rid of. I see a plus 1, a 3, and a minus 4. So the positive 3 in the front, since 3 is bigger than 1, that's going to be a vertical stretch by a factor of 3, which means I'm going to get skinnier. The negative 4 on the inside means I'm going right 4, and the plus 1 on the outside means I'm going up 1. So my original quadratic is a U with its vertex, or its lowest point, at 0, 0, right in the middle of that Cartesian plane. However, now we're going to make our U move to the right 1, or right 4, up 1, and then get a little skinnier. In Unit 1.3, we were evaluating and operating on functions. So we were able to describe the process of operating and evaluating functions, including adding, subtracting, multiplying, dividing, and composition. So to add and subtract functions, we have to pay attention to the order, because while it doesn't necessarily matter for addition, right? 4 plus 2 is the same thing as 2 plus 4. It does matter for subtraction. 4 minus 2 is not the same as 2 minus 4. So in this case, we're doing f plus g, which means I need to write f of x plus g of x, not the reverse. So for addition, I'm going to write x plus 1, and I'm going to add that to g of x, which is negative 3x squared minus 2x minus 1. So we need to identify our like terms, our stuff that looks the same. And in this case, the x and the minus 2x are like terms, and the positive 1 and the negative 1 are like terms. There's no pair for the negative 3x squared. So in essence, the negative 3x squared is paired with a 0, an invisible 0. So we have 0 plus negative 3x squared. That keeps it at negative 3x squared. We have 1x plus negative 2x. That's going to be a negative 1x. And then we have 1 plus negative 1, which is just 0, so we don't even have to write it. When we get to subtraction, it's a little tricky with that negative. So if you can remember to always keep that negative, you shouldn't have a problem. But if you need to, you can distribute the negative through and therefore create it as an addition problem, which makes it a little more straightforward. I'll run through both. So again, we have f of x minus g of x. Our like terms are still the same. So again, we have that invisible 0 being paired with the negative 3x squared. So our first term would be 0 minus negative 3x squared. In other words, 0 plus 3x squared, which is just 3x squared. We have 1x minus negative 2x, which is the same thing as 1x plus 2x. So that's our 3x. And then we have 1 minus negative 1, which is 2. However, if that negative is going to be confusing, let's go ahead and distribute it through the g of x. So our f of x stays the same, and we take that negative from the in front of g of x, and we distribute it. So negative, invisible 1, so negative 1 times negative 3x gives us positive 3x squared. Negative 1 times negative 2x gives us positive 2x, and negative 1 times negative 1 gets us positive 1. What we've done is transform this subtraction into a simple addition problem, where again, we simply combine like terms. Multiplication is a little bit trickier, although it doesn't matter the order again. So like addition, 4 times 2 is the same as 2 times 4. But just for clarity, we're going to keep it as f times g. So there are multiple ways to do multiplication. Multiple ways to do multiplication. I prefer the box method as opposed to distribution. Sometimes with distribution, it gets a little complicated, so the box is a clear way of organizing my thinking. The box method works by differentiating your box into the number of squares as you have terms. So my f of x has 2 terms, the x and the plus 1. So I'm going to draw 2 rows, one with x and one with plus 1. Then I have g of x, which has 3 terms. So I'm going to create 3 columns, negative 3x squared, negative 2x, and negative 1. Then I'm going to go through each of the boxes and multiply the terms that meet in those boxes. So from left to right and then top to bottom, we have x times negative 3x squared. That gives me negative 3x cubed. We have x times negative 2x, which is negative 2x squared. And we have x times negative 1, which is negative 1x, or simply negative x. On the bottom, we have everything being multiplied by positive 1. So anything multiplied by 1 is just itself. So I'm just going to leave it and bring it down as negative 3x squared, negative 2x, and negative 1. Now, I just take everything that I multiplied and put it into a line. So reading from left to right in the top row and then left to right in the bottom row, it would be negative 3x cubed minus 2x squared minus 1x minus 3x squared minus 2x minus 1. In this case, what you see is me going down the columns. So negative 3x cubed minus 3x squared minus 2x squared minus 2x minus x minus 1. Already my like terms are grouped together, but what are my like terms? There are 2 of them. One of them is negative 3x squared and negative 2x squared. Those are going to combine to form negative 5x squared. The other pair of like terms is negative 2x and negative 1x. Those are going to combine to form negative 3x. So my final product for multiplication of f times g of x would just be negative 3x cubed minus 5x squared minus 3x minus 1. Division is by far, in my opinion, the simplest of the 4 operations we're going to see yet. It will get harder in later units, but for now, all I need you to understand is that you need to set f over g. So it's going to look like a fraction. Be careful because like subtraction, it does matter which one's on top. In this case, it says f over g. So f has to be on top. If nothing cancels, you leave it as it is and you move on. Composition is a little more difficult and it goes along with how we evaluate functions. So it's read as follows, f of g of x. So we're plugging in a function into another function. So when I say evaluate f of x at 2, what I'm saying is plug in 2 everywhere you see an x. But now I'm saying f of g of x. So everywhere you see an x, you're going to replace it with g of x. The same is true for g of f of x, so you would substitute f of x into g of x equation. So in the top, it says f of g of x. In other words, I'm taking g of x and I'm plugging it into f of x. Remember, f of x was x plus 1. So instead of x plus 1, I'm putting g of x plus 1. And then I'm simplifying. G of f of x, however, is slightly more complicated because g of x had a couple x's. It had negative 3x squared minus 2x minus 1. So now instead of x, we are replacing x by putting in all of f of x, which was x plus 1. So my new function would be negative 3 times x plus 1 squared minus 2 times x plus 1 minus 1. And then I'm going to simplify. So you see on the right, I've created my box to do the multiplication. I've also distributed the negative 2. So it's negative 2 times x and then negative 2 times 1. And then I've combined my like terms to simplify. So now that we know how to operate on functions, we can evaluate them. And to evaluate a given function at a given x value, you need to substitute or plug in that x value into the function and simplify. This will ultimately help us graph functions. So let's look at this example. Let f of x equal x squared minus 5, and we need to evaluate it at 0, 2, negative 1, and 5. But let's think about our transformations. Let's go back to Unit 1.2. What would be the parent function of this graph? If you said quadratic, you're correct. What letter does the graph of a quadratic look like? It looks like a U. Now, I see a negative 5. So what do we know about a negative 5 being on the outside? A negative 5 on the outside is going to move the graph down 5. So we're going to confirm what we already know the graph should look like by plugging in points and plotting them on our graph. So if I want to evaluate f of 0, everywhere I see an x, I'm going to put a 0. So my new equation would be 0 squared minus 5. 0 squared is just 0, minus 5 would give us negative 5. F of 2 means that everywhere I see an x, I'm putting a 2. So now I have 2 squared minus 5, which comes out to be negative 1. For f of negative 1, I have negative 1 squared minus 5, which becomes negative 4. Now here's where you have to be careful, because if you put negative 1 squared in your calculator, you have to make sure you put parentheses around the negative 1. Otherwise, your calculator will do 1 squared and then put the negative back. Therefore, it will tell you that negative 1 squared is negative 1, which we know is not true. So to keep that from happening, I always put parentheses whenever I'm substituting in an x. I want you to do f of 5 on your own. Once you have these points, you'll plot them. So you'll plot the point 0, negative 5, 2, negative 1, negative 1, negative 4, and then 5, comma, 20, because 5 squared minus 5 is going to be 20, and therefore you'll see that the u of the quadratic has indeed shifted down 5. So these last two examples are adding our functions again, and then it also combines that with evaluating that new function at 10 or at 1. So we need to add f of x plus g of x. So I'm going to add 3x plus 3 and negative 4x plus 1. I need to combine my like terms, so I need to combine 3x and negative 4x to give me negative x, and I need to combine 3 and 1 to give me 4. So my new function, f plus g of x, is negative x plus 4, but we're not done because it says to find it at 10, so not just x, at 10, which means I need to substitute in 10 everywhere I see an x. So again, when I plug something in, I put it in parentheses. So I have negative 10 plus 4, which is negative 6. Go ahead and try the right example on your own. In Unit 1.4, we talked about piecewise and absolute value functions. Our objective was to be able to evaluate and graph piecewise and absolute value functions, and we wanted to be able to relate them to one another. So an absolute value function is a function with the equation f of x equals, and then it has the absolute value bars around the x. Remember that an absolute value of a number is its distance from 0, so it's always non-negative. Why can't we say it's always positive? What would the absolute value of 0 be? Is that number a positive number? Can you say that 0 is a positive? Not really. So you have to say that an absolute value is simply non-negative. It's the distance away on a number line from 0. So let's do a couple of examples and review again our parent functions and our transformations. In this case, both of our parent functions are absolute value functions. Those are fairly obvious given that we have the bars. So we know our general shape is a V. On the left example, we have a +1 on the inside. That means it's going to shift to the left 1. But just to confirm what we already know our graph is going to look like, let's plug in some x values and see what we get. When I plug in -2, I get the absolute value of -2 plus 1. That means I have the absolute value of -1. And -1 is 1 away from 0. So I would plot the point -2, 1. When I plug in 0, I get the absolute value of 0 plus 1, which is also 1. When I plug in 2, I get 3, and when I plug in 4, I get 5. So after plotting those points, that's what my new function would look like. And it does indeed match what we thought, a V shifted to the left 1. On the right example, our +1 is on the outside, which means it's going to go up 1. But let's confirm by plugging in a couple values. These are arbitrary numbers. You can plug in whatever you want. I usually try and do a couple negative, 0, and a couple positive. So when I plug in -1, I get the absolute value of -1 plus 1. The absolute value of -1 is 1. So 1 plus 1 is 2. When I plug in 0, I just get 1. When I plug in 1, I again get 2. And when I plug in 4, I get 5. After plotting those points, the graph indeed did move up 1. The last example combines two transformations. So the positive on the inside is going to move us left 1, and the +3 on the outside is going to move us up 3. When I plug in -3 into my equation, I get the absolute value of -3 plus 1, which is the absolute value of -2, which is 2, plus 3, which is 5. When I plug in 0, I get the absolute value of 0 plus 1, or the absolute value of 1, which is just 1, plus 3, which gives me 4. When I plug in 2, I get the absolute value of 2 plus 1, which is the absolute value of 3, which is 3 plus 3, I get 6. And for lastly, absolute value of 3 plus 1, which is the absolute value of 4, which is 4 plus 3, which is 7. So my graph, again, we are correct, saying it's going to move left 1 and up 3. If we wanted to graph or just evaluate absolute values on your calculator, you need to hit alpha, the green button, and then click F2, which is located above the window button. At that time, shortcuts will pop up, and the first one says ABS parentheses. That stands for absolute value. So go ahead and click 1 or enter, and you'll see that the absolute value bars come up. So we're going to learn how to convert between absolute value and piecewise functions. So we're going to find where the absolute value part of the expression is equal to 0, and then we're going to create a sign chart or a number line. We're going to plug in a value bigger than the x value we solved for in number 1, and we're going to plug in a smaller value and see if it's positive or negative. Depending on whether it's positive or negative, decides whether our slope is going to be positive or negative. Keep in mind that the absolute value graph has a positive slope going upwards and a negative slope coming downwards. So in essence, it's two lines meeting at a vertex. So let's go through this example. We need to write f of x, which equals the absolute value of 2x plus 4, using inequalities. We're going to convert it to a piecewise, essentially. So step 1 said set the inside part equal to 0 and solve for x. So I'm going to solve for x. I'm going to move the -4 over, and then I'm going to divide by 2, so I get x equals -2. Then I'm going to create a sign chart where I put in a value less than -2, and I'm going to put in a value greater than -2. So for example, I'll use 0. I'll plug in 0 as a value bigger than -2. When I plug that in to 2x plus 4, I get a positive number. 2 times 0 plus 4 is a positive 4. so I put a little plus on the right side of negative 2. When I plug in a number smaller than negative 2, say negative 3, I get 2 times negative 3, which is negative 6, plus 4, which is negative 2. Again, that's a negative number, so I put a little minus on the left. Therefore, when I create my piecewise function, I have, for numbers smaller than negative 2, a negative slope, and for numbers bigger than negative 2, I get a positive slope. Notice it doesn't matter whether I said it was less than or equal to negative 2 for either equation, because both are going to meet at the same point. So you try the right-hand side one on your own. Here are a couple of examples of piecewise functions. The one on the left is just an equation, but again, you can see the negative slope of when x is smaller than 7 and the positive slope when x is bigger than 7. On the right-hand side is a graph with 3 separate equations for 3 different functions of your piecewise function. So piecewise functions are functions defined by multiple equations over a specified domain. So let's use this example to see which equation we would use to evaluate when x equals negative 1, x equals 0, and x equals 1. When x equals negative 1, we use the first equation because negative 1 is smaller than 0. When x equals 0, we'll use the second equation because 0 would be greater than or equal to 0. When x equals 1, we're going to use the second equation again because 1 is greater than or equal to 0. After you've determined which equation you're going to use, you can then plug in your x value and solve. Here's an example of a piecewise function. I want you to tell me what its domain and range is, whether it's a function or not, and what it would be evaluated at negative 2, 6, and 1. So at negative 2, I need to use the second equation because negative 2 is smaller than 1. So I would plug in negative 2 to x squared plus 3 and get negative 2 squared plus 3, which would be 7. When I'm told to evaluate at f of 6, I need to use the first equation because 6 is greater than or equal to 1. So we're going to plug in 6 into 2x plus 1 and get 13. When I'm told to evaluate f of 1, I need to use the first equation because 1 is greater than or equal to 1. Therefore, I would get 3. To write a rule for this function shown on the left, we need to first determine how many different lines we see. I see 3 different lines. Therefore, I have 3 different functions. Let's determine now the intervals of each of those functions. The first one goes from negative infinity all the way to negative 4. The second goes from negative 4 to positive 2, and the third one goes from 2 to infinity. Now we can look at each of them respectively and find their corresponding equation. So the first one on the far left, from negative infinity to negative 4, it's always going to be 2. So my value is 2. For that middle equation, from negative 4 to 2, we've calculated the slope as being negative 1. It goes up 1 and left 1. So in other words, moving from left to right, it goes right 1, down 1. So that's a negative 1 slope. And its y-intercept, where it crosses the y-axis, is minus 2. The last line on the far right, it has a positive 1 slope, and it would cross the y-axis at negative 6. To solve an absolute value function, we need to first understand what it's saying. All right, if I'm looking for an absolute value being equal to a certain number, say in this graph, I'm looking for the value for which the absolute value equals 6, I'm going to draw a horizontal line at 6 and see where it crosses. It crosses at 2 points. It crosses at 6 and it crosses at negative 6. So that corresponds to the right-hand number line where I've got 2 dots. Now, what if I said, where is the function greater than or equal to 6? If I said it was greater than or equal to 6, it would have to be above the horizontal line that you drew. So that would correspond to anything bigger than x equals 6 or anything smaller than x equals negative 6. If I said for what values is it less than or equal to 6, you would tell me it's in between negative 6 and 6. The difference between an open circle and a closed circle simply means whether it's included or not. If it's a greater than or less than, it is not included. But if it's greater than or equal to, or less than or equal to, it is included. To solve for absolute value equations without a graph, you need to create two equations, one positive and one negative, and then solve each corresponding equation for the x values that satisfy the original equation. On the equation on the right, we have 3x minus 2 equals 19. So we set one of them equal to positive 19 and the other equal to negative 19. This would be the same as, if you would prefer, you can do 3x minus 2 equals 19 and negative 3x plus 2 equals 19. And then continue to solve each one of them for x, and those would be your solutions. The practice problem at the bottom is actually impossible to solve. Why? Let's think about our transformations. We have an absolute value function being reflected and moved to the right 3. Therefore, will it ever cross at 12? No. An upside down v is always going to be in the negatives. It's never going to cross at at positive 12. Therefore, there would be no solution. There's no x value I can put in that would give me 12 as the answer to that equation. Again, here's another example. So if we were to graph it, we would graph the function absolute value of x plus 2. In other words, a v shifted to the left 2, and we would find all the values for which it was smaller than 4. We would draw a horizontal line at 4 and shade in all of those x values that are below 4. If we wanted to solve it mathematically, however, we would say, okay, we have values that are less than 0 and values that are greater than 0. Let's solve each of those for x to determine what are my intervals. So at x is smaller than or equal to 2, and when x is greater than or equal to negative 6. So somewhere between negative 6 and 2, our absolute value function is smaller than or equal to 4. This makes sense. If you don't believe me, graph it. Here are a few more examples for you to try on your own. Make sure that you keep in mind the positive and negatives. Make sure to keep them straight, and if you need to reference the slide before to determine what your solution is going to look like, feel free to do that. In Unit 1.5, Inverse Functions, we are going to learn how to calculate inverses and know the steps for solving inverses, as well as how to determine whether a function has an inverse. In Unit 1.5, we started talking about inverse relationships. So there are two different types of relationships: a direct relationship, as x increases, y increases, or as x decreases, y decreases. As an example, as you study more, your grade improves. As you study less, your grade decreases. An inverse relationship, though, is that x increases, y decreases, or as x decreases, y increases. They're kind of opposite. An example of this is when I do more work in class, I have less homework at home. Inverse functions undo one another. So some examples in everyday life would be untying your shoe as the inverse of tying your shoe, making your bed in the morning as the inverse of getting into your bed at night. But if you're a function, say f of x equals x plus 3, the inverse, said f inverse of x, or f to the negative 1 of x, would be x minus 3. An inverse function is a function that will undo anything the original function does. It can be written as y to the negative 1 or f to the negative 1, and it's said f inverse of x. Some inverse operations that we've already seen are negative, or division counteracts multiplication, positive counteracts negative, both of those are vice versa. Square rooting something counteracts squaring something, the vice versa is true. X squared, square rooted, cancels each other out. And taking a over b is the inverse of taking b over a. In other words, if I have a fraction, 3/4, I would get rid of it by multiplying it by its reciprocal, 4/3. If the point AB is on the graph of f of x, then the point BA is on the graph of f inverse of x. Because you're switching the x and y values, the domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. So let's go back to our A and B example real quick. The domain is A and the range is B. But in the inverse equation, B was our domain and A was our range. So looking at the example on the bottom, we've got a set A and a set B. If I wanted to write them as coordinate points, I have 1, 5, 2, 6, 3, 7, 4, 8. But its inverse would be 5, 1, 6, 2, 7, 3, 8, 4. If you're given coordinate points or a graph, all you need to do to find the inverse is just switch them. Do not change the sign, just change which one comes first. So if I have the coordinate points 1, 2, 4, negative 2, 5, 6, 99, negative 22, all I need to do is switch them. 2, 1, negative 2, 4, 6, 5, and negative 22, 99. There is a mistake there. On the graph, I see 3 points being labeled. So if I want to create a new line, I'm going to find the inverse of those points. The inverse of 0, 5 is 5, 0. So I plot the point 5, 0. The inverse of 3, 3 is still 3, 3. So I leave my point there. And the inverse of 6, 1 is 1, 6. Notice that the inverse reflects over the line y equals x. A horizontal line test is similar to our vertical line test, right? It has a very similar name, but it is not the same. A horizontal line test tells us whether or not a function has an inverse. What does the vertical line test tell us? If a horizontal line crosses the function more than once, that function is not one-to-one and therefore cannot have an inverse. Let's determine if these are one-to-one. One-to-one means that you can't have two different x's going to the same y. Each one has to go somewhere different. That interferes with our third requirement of a characteristic of a function. In this case, all of our arrows go somewhere different, so that is one-to-one. This is a linear function. If I draw the horizontal line anywhere I want, it only crosses once, so that again is one-to-one. However, this piecewise function would look like it's one-to-one if I drew my horizontal line at, say, 2, but as you move up, it looks like the horizontal line would cross more than once, and therefore it is not one-to-one. The table we can tell by determining whether or not it has the same y value. This looks like it's going to be a quadratic. If I were to plot the points negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4, it would come up to be a U shape, and therefore would not be one-to-one. So which of these graphs would have an inverse and which one would not? In other words, which ones are one-to-one and which ones are not? It looks to me that the only one that is not one-to-one is the quadratic at the top right. All of the rest, no matter where I draw my horizontal line, it will only cross once. Which ones would pass the vertical line test, though? Only the ones on the right-hand side would pass the vertical line test. In other words, the ones on the left, the absolute value one kind of on its side and the squiggly one, are not even functions. They're just relations. Can we take the inverse of an absolute value or a quadratic? If I do the horizontal line test, it crosses more than once. So how can we have the square root, which is the inverse of x squared, how can we make that possible? Remember that the square root function looked like just one part of a quadratic. It didn't look like a u on its side, it just looked like half of a u on its side. So in order to take the inverse of these functions, we need to restrict the domain. In other words, we need to cover up half of the function and only take the inverse from 0 to infinity. That allows us to have inverse functions. There are 4 steps to solving inverses. The first is to replace f of x with y in the equation. The second is to switch x and y. The third is to solve for y. And lastly, to replace y with f inverse of x. So let's work through this example on the right. The first step is to replace f of x with y. So now it reads y equals 2x minus 5. Then we need to switch our x and y, which means all of our x's become y's and all of our y's become x's. Thirdly, we need to solve for y. We need to isolate y by adding 5 to both sides and then dividing by 2. Once we've isolated y, the last step says to replace it with f inverse of x. So the inverse of 2x minus 5 is x plus 5 over 2. Here are some good workbook pages for additional practice in preparation for your exam.